This is RTP. This is RTP180.
So, hi everyone. Thank you for coming, and thank you for the invitation to present here this evening. And a special thank you to Dan, who just gave a fantastic introduction to quantum computing, which makes my job up here significantly easier. So, quantum computing versus quantum information science. What is the difference? That is where we're going to start this evening. So, quantum mechanics emerged as an area of physics a little over 100 years ago. And it emerged in response to a lot of very puzzling results that were coming out of both physics experiment and physics theory. In the time since then, it has matured greatly as a field and has given us numerous advances. It's given us the laser, it's given us transistors, it's given us magnetic resonance imaging, or MRI, which is incredibly useful for medical imaging and a lot of other applications. And it has been an enormously beneficial and pivotal development for physics. Kind of in the 1970s, people started to have the idea of, what if we combine some of these ideas from quantum mechanics with computer and information science? So one of the first ways that this manifested was from physicist Richard Feynman, who was thinking about the problem that Dan actually articulated with, if we want to simulate very complicated systems that are based in the rules of quantum mechanics, maybe a normal computer isn't ideally suited for those tasks, and we're going to be we're going to have a greater advantage at simulating those systems if we use systems that are rooted in quantum mechanics itself. So that is the field of quantum simulation. A little bit later, people started to think about applications like we're asked about in the last Q&A, relating to kind of cryptography applications. And an algorithm was developed that could crack certain encryption codes significantly faster if you had a quantum computer to run that algorithm on than you could ever crack that code if you were running similar decryption algorithms on a classical computer. So there were enough indications that there were going to be useful applications for these quantum systems that we tried to start building them. This was mostly done within the realms of physics laboratories, and physicists learned very quickly that we are very bad engineers for the most part. So engineering sciences were brought into the fold. And when you combine all of these three areas, so quantum mechanics, computer and information science, and engineering, you get the discipline of quantum information science, which encompasses everything that Dan was talking about, but also broader areas. And that's where I'm going to try and get to in this talk. So what are we actually doing in these systems, though? What really makes this quantum mechanics the pivotal difference in our ability to process information, gather that information, and share that information in revolutionary kinds of ways? So to understand that, we have to meet the qubit, which was also referred to in the Q&A session. So in order to understand what a qubit is, we have to start by really understanding what a classical bit of information is. So classical bits are the basis for all modern computers. So everything from a supercomputer to your laptop or desktop to what's in, I'm pretty sure, everybody's pocket right now, your smartphone. These bits are physically made of semiconducting transistors. And these transistors have the property that they always have to be on and off. So you can think of this kind of like a light switch. So here's your cartoon schematic of a transistor on the bottom, and it's either going to be in an on state or an off state. And if you combine these on and off states creatively through algorithms, you can run those algorithms on a computer, and you have all of the novel applications from gaming to sending your emails to anything else you would like to do on these systems. So quantum bits are a little different. They are based in the rules of quantum mechanics, and they're physically made of quantum mechanical objects, so things like atoms or ions. And very dissimilar to the classical bit, these do not always have to be off or on. So to stick with the light switch analogy, we can kind of think as a qubit as like a light switch with a dimmer on it. So it can be either all the way on blazing light, all the way off completely dark, or really anywhere in the middle. And when you start to leverage that property with other properties from quantum mechanics, also like Dan mentioned, we have things like entanglement, which is very crucial in quantum algorithms, and also this wave-matter duality, this bizarre feature that quantum mechanical objects have where they can act like a wave and a particle at the same time. And when you combine these phenomena together, you can start to build things like quantum computers or other quantum information kinds of implementations. So what are some of those implementations? We have these qubits. What are they good for? So first and foremost, we have quantum computing, which Dan did the excellent job of talking about, which is the application that most people are typically familiar with. So I wanted to show this picture, even though Dan already showed you kind of the inside of a quantum computer, for two reasons. One, this is an earlier implementation of one of the IBM systems that he talked about, so you can kind of see how things are evolving a little bit. Also, I really like this picture because there are two women in it. And these, yeah. And these are genuine IBM researchers. I know both of them. This is not a staged photo. So when I'm not thinking about quantum information science and quantum mechanics, one of the things I think about is how can we get more women interested in this area and in this field? So if anybody is interested in that, I'm also happy to talk about that. The second application that most people are familiar with if they start to look into quantum information science is also what we talked about in the beginning of this talk with Richard Feynman's idea, and that Dan also referred to, kind of these quantum simulations. So beginning to understand what is going on in very complicated materials or very complicated chemical reactions by really leveraging the quantum mechanics that's underlying those dynamics. But what else can we do? So one of the things that I'm very interested in as I manage my quantum information science portfolio is quantum sensing. So using qubits as very sensitive probes of the environment. So here I have two images. This, if I get the laser right, this is a setup at Harvard that's using nitrogen vacancy-based qubits for very sensitive magnetic measurements. So they're looking at everything from rocks to meteorites to explore geology and space kind of questions. This second one is a setup at Stanford University that is using quantum sensors for very precise probes of general relativity and gravity to try and push the limits of our understanding of fundamental physics. We can also start thinking about connecting qubits not in just ways that enable quantum computation, but also distributing quantum information and looking at how can we really gather information and process it and then share it on large scales in ways that we can't do if we have these systems just composed of classical bits. And then the final part of this is just a big and. So one of the most exciting parts of my job is getting to think about additional ways that we can use qubits to really push information science into directions that we haven't even begun to think of. And this is one of the things that we're very excited to get out and talk to people in other communities with creative ideas to see if, just like we did in the beginning by combining quantum mechanics with information science with engineering, we can start to combine other areas and realize truly novel applications of these systems. That's all. I'm happy to take any questions.